Okay, so now for this lesson, we are going to focus on this thing called wavefronts. Okay, so what is wavefront? Before that, let's just watch this simple animation. Okay, so basically, I'm going to turn on the tab, right? And what you expect to see is as the water droplets goes to a tank of water. Okay, you get this thing, right? This very common looking thing. You all should be quite familiar with this. This is known as a waveform. Okay, so just to define first, this thing that we've been drawing for the past few lessons, this thing is known as a waveform. All right. Okay. Now, and clearly, of course, if we increase the amplitude, what you will expect to see is that you realize the water is higher than before as compared to say when the amplitude is low, or yeah, maybe something like that versus something like this when the amplitude increases, right? So you realize the up down, the distance from the equilibrium, which is the center line, okay, or the highest point to the equilibrium is larger when the amplitude is higher, right? And of course, when the frequency goes up, what you expect to see is that in a shorter amount of time, you actually get more waves, okay, versus when the frequency is low, and then you realize what actually happens, right, is that the water droplet, the amount of time it takes to produce one water droplet is now lesser. Okay, hence the number of wave that you get is also lesser every second. Okay, but if you increase the frequency, what you realize is that the water droplets drop at a very fast rate. This creates more waves every second. Okay, so that's the idea of frequency and amplitude. Just to recap quickly what we went through the last lesson. Okay, and this is a waveform. Now today I'm going to teach you all this thing called the wavefront. Okay, as the topic suggests. Now what is a wavefront then? Okay, so basically, right, this is the side view of a water tank. Now as a water droplet drops on a water tank and we look at it from the side, it's going to look something like that. However, if we look at it from the top, right, we get this kind of effect, right? These are known as water ripples. Now the light blue parts, they are known as your water ripples. Now these light blue parts, right, they are also gonna be called the wavefronts. Okay, so what exactly the wavefront? We'll discover that later. Okay, but over here, what I want you to know, right, is that these light blue parts, they are known as wavefronts. Okay, and they are imaginary lines. Yeah, they don't really exist. It's more like we perceive it to exist. Okay, so they are imaginary lines, and you realize, right, if I put my cursor here, okay, so somewhere around this part of the screen, you realize if I go to the side view, over here, it corresponds to this thing. This is known as the crest. If I put my cursor here, right, okay, so I want you to focus your eye on this part of the screen, and I change it to the top view, you realize it corresponds to the light blue part of the wavefront. Okay, so you realize that the crest is actually represented by the wavefront. And so there's a single wave here, there's also another wave here, and there's another wave here, and in fact there are many waves, okay, they are traveling outwards. Okay, so all these number of waves, right, when you combine all the crests together, what you get, right, is actually an imaginary line, and this line is called the wavefront. Okay, so basically what is the wavefront? The wavefront is the line that joins all the peaks of a wave. Okay, so what is the peak of a wave known as? Because this works for a transverse wave, this is called the crest. So the line that joins all the crests on a wave is called the wavefront. Okay, so once again, take a look. Okay, so I'll turn on to the side view. I want you to focus on the crest. Okay, so at any point I'm going to pause, so maybe I pause here. I want you to focus on the three crests here. Okay, so focus on the three crests. Okay, maybe you can take your finger and just like lightly touch the 3 points where you want to focus on, and then as I turn it to the top view, right, you realize the 3 points that you are touching on, right, corresponds to the 3 wavefronts here. In other words, this is a single wave that you see from the side view. If you look at it from another side, you also see a wave like that. If you are able to see multiple waves, okay, and you are going to use a line to join all the crests of these waves that you see together, what you get, right, is a wavefront. Because this line here probably represents the one that we saw just now, but this line here represents another graph, and the graph actually looks the same. I mean the waveform actually looks the same. But if we join the multiple infinite number of waveform that we can see, okay, we join all the crests together, we actually get a wavefront. And this is the idea, right? So what is a waveform again? Waveform is just this. this is a waveform. Over here, this is a waveform. And why is a wavefront? Wavefront is seen over here. So they are just the circular rings, right? The light blue circular rings. Okay, so that's the idea of a wavefront versus a waveform. Okay, so water waves are easily produced and observed by touching one point on the surface. What happens is a disturbance is created. Okay, which produces waves. Okay, so basically how to create wave, we first need to create a disturbance. Okay, a disturbance can come in the form of touching water, like in this photo, or just simply by switching on the tap, like in this animation, right? Okay, now the direction of wave, travel of wave is always perpendicular to the wavefront. Okay, what I mean is you can write this here. Okay, so what happens is, if let's say I have a circular wavefront, right? Okay, let me draw a proper circle. Hold on. Okay, so let's say I have wavefronts like that. Okay, so where is the source? The source will be here. Okay, and how is the wave traveling? The energy is flowing outwards. Okay, so the wavefront is always perpendicular to the wave travel. So this red color one is the wave travel. Now the wavefront are the blue ones. Okay, you have learned in math how to deduce tangent of the circle. So the tangent to the red color one, the tangent of the second circle to the red line is here, and you'll realize that they are perpendicular. So the tangent of the first circle to the red line is here. The tangent of the third circle to the red line is here. Okay, and they are all perpendicular to each other. And this is what I mean when I say the direction of the travel of wave is always perpendicular to the wavefront. Okay, so the red line represents the wave travel. The circles obviously represent the wavefront, and you realize that they are all perpendicular to each other. Okay. Okay, so transverse waves are produced when by touching water surface with a wooden bar. Sorry, this is not transverse wave, this is called plane waves. Okay, so plane waves are produced by touching the water surface with a wooden bar. The wavefront of the wave plane waves are also perpendicular to the wave travel. Okay, so basically I have a wooden bar moving up and down. What happens is that I'll create a wavefront that is that are like just horizontal rows. Okay, so these are actually your wave fronts. Okay, these 5 lines here. Okay, these 2 lines here, they are known as your wave form. Okay, and the wave is obviously okay, I'll use the red one to represent again. The wave is obviously traveling this way. Okay, now the red one represents wave travel, and as you can see, they are all perpendicular to each other, and hence our statement is true still. The direction of travel of wave is always perpendicular to the wavefront. Okay, now the next part, right, is actually on the reflection of wave, and the reflection of wave is quite similar to that we learned in light. Okay, so remember in light, the law of reflection, you say that the angle of incidence is equals to the angle of reflection, right? Okay, so angle of incidence equal to angle of reflection is the same thing here. So you realize the incident water waves comes in here, gets reflected, and the 2 angles are actually the same. Okay, what is different here is that there are wavefronts to be drawn. Okay, so all these lines that you see, okay, I'm going to highlight them. Okay, so this line, all these lines that you see, right, they are actually your wavefronts. Okay, including the dotted line. So the dotted line are the reflected wavefronts, the solid line are the incident wavefronts. Okay, not that it's any different, they are in fact the same, but I just want to give it a name here. Okay, so the incident wavefronts are here and the reflected wavefronts are here. Okay, you'll realize something very important to take note of here is that the gap between the lines, they are actually equal. Okay, now what does the gap represent? Remember, right, that wavefront is from one crest to another. Okay, so what is one wavefront? One one wavefront will be counted from this light blue to another light blue. This is known as these are two wavefronts. Okay, and the distance between two wavefronts, right, as you can see here, are the distance between two crests. And if you remember, you can recall, the distance between two crests is also known as one wavelength. Okay, and hence you should, maybe you should write down, yeah, let's write here. Okay, so this is important. Take note that the distance between two wavefronts is equals to one wavelength. Okay, and reflecting does not change the wavelength. Yeah, obviously, right? Reflecting can't change the wavelength. In fact, reflecting doesn't even change the speed or the frequency. So what happens is that the distance between two wavefronts must be the same. It will still be one wavelength. Okay, and if you use your ruler to measure, if this happens to be 1 cm, this must also be 1 cm. Okay, so when water waves get reflected, the only thing that changes is the direction. Okay, so frequency and wavelength are the same throughout. And why did I say that the velocity is the same? So recall that v equal f lambda. So if f and lambda are constant, then clearly v is also going to be a constant. Okay, so yeah, that's it for this page. What I want to do now is to actually you can cross out this part. I'm not going to teach this part. Okay, this part is for the pure physics students. Okay, then I want you to draw a line here. Okay, and just right here as a wavefront practice. Okay, so I'm gonna go through one question with you, and then after that we'll end this video here. Okay, you can also cancel this part. Okay, this part is not being taught. These are for pure physics students. Okay, and I need you to take note of the EM spectrum. I need you to focus on this page for the upcoming test. Okay, and if after I finish teaching Wavefront, you should be able to do all the questions here. So please remember to do your tutorial from page 17 onwards. Okay, so okay, let's go through the Wavefront practice now. So basically what we want to do, right, is to learn how to draw Wavefront. And actually drawing Wavefront is quite simple. Okay, so most wavefronts that you are required to draw are plane waves. So what are plane waves again? Plane waves are waves that are created by an up-down motion of a bar, and you realize your wavefronts, right, they are actually just straight lines. Okay, so you don't have to draw the circular wavefront. Most of the time we only want you to draw the straight line wavefronts, okay, which are quite simple. So if let's say I have a graph, right? Okay, so let me draw out a displacement distance graph. So let's say I have a graph that's like this, right? So this is displacement distance. Okay, so what we have here is just a very nice just a very nice waveform. Okay, so something like this, right? If let's say the amplitude is 1, okay, and what we have here is 4, 8. Okay, first thing you need to identify is that the lambda is equals to 4 meters. So the wavefront is 4. Okay, the question will probably be draw 5 wavefront to represent the wave. Okay, so draw 5 wavefront to represent the wave. Okay, so what you do, right, is the first thing you need to do is to come up with the scale. Okay, so what's the scale? The scale will probably be something like 1 cm is to 2 meters. Okay, so to represent 4 meters, we need 2 cm. Now there are 5 wavefronts to represent the wave. So basically you expect yourself to have 5 lines, right? So to have 5 lines, now 1 cm is to 2 meters. You realize that what you need to do is first you need to draw a line. Okay, this will be your first wavefront. So just draw a line like that. This will be your first wavefront. Okay, yeah, draw it straight. Okay, doesn't really matter how long. Okay, just not too long, not too short. Okay, the next thing you need to do, right, is I need you to take a ruler, and I want you to measure this to be 2 cm. Okay, this doesn't need to be represented, doesn't need to be drawn out. Okay, you don't have to label this. Okay, I'm just writing here for clarity purposes. Okay, so this needs to be 2 cm. So after you measure it to be 2 cm, you draw another wavefront. And same thing, you measure 2 cm again and you draw another wavefront. You measure 2 cm again, you draw another wavefront. And the last one, measure 2 cm again and you draw another wavefront. And then that's it. That's your answer. So these are the 5 wavefronts. Okay. Now take note of a few things. Number one, each gap is 2 cm. Why is it 2 cm? It's because this gap represents wavelength and the wavelength equals to 4 meters. The second thing you must take note is that each wavefront must be parallel to each other. Okay. Yeah, remember that the wave travel must be perpendicular. So hence, if the wave travel is one straight line, and if the black lines are not parallel to each other, then what you have is this. You actually have this that is not 90-degree, and this cannot work. Okay, so this person, this answer is actually wrong because of this line. Yeah, so this is wrong. Okay, so you must make sure that they are all parallel to each other. That means they must all be vertical. Okay, yeah, so that's how you draw wavefront, and actually end the video here. Okay, if there's any question, you can let me know in class when we meet. Okay, otherwise I'll end the video here. Okay, thanks for watching. Okay, bye.